Hello and welcome to Regular Expression Deep Dive. In this video we're going to cover a lot, including what a regular expression is, understanding the Regex engine, special characters, character classes, negated character classes, shorthand character classes, negated shorthand character classes, the dot, capture groups, anchors, word boundaries, alternation, backtracking, backreferences, look ahead, look behind, and more. Each chapter will be timestamped in the description, so if you're interested in a particular feature of regular expressions, then feel free to skip to that chapter. This tutorial will focus on the JavaScript implementation of regular expressions. So, what is a regular expression? A regular expression, also referred to as regex or simply expression, is a sequence of tokens that forms a pattern. The regex engine then searches a string for matches of that pattern. The simplest tokens consist of a single literal character, but some tokens consist of multiple characters, for example the word boundary token, which consists of a backslash followed by a B. I'll be using a website called regexr.com in this tutorial. It's very helpful for debugging and practicing your regular expressions. I'll include a link to it in the description to this video. I'll start by explaining the format of an expression. There is a forward slash before the expression and a forward slash after the expression. The tokens between those forward slashes are the expression. Also, any enabled flags are represented by a letter after the forward slash at the end of the expression. There are two types of flags. The first type affects the way the engine interprets the expression. For example, the case insensitive flag. By default, when the engine compares a token in the expression to a character in the string, it performs a case sensitive comparison, meaning they only match if they are both the same case. If you enable the case insensitive flag, then when the engine compares a token in the expression to a character in the string, it performs a case insensitive comparison, meaning that they match whether the case is the same or not. The second type of flag affects the way the engine performs the search. For example, the global flag, represented by the letter G, means that instead of the engine stopping after it finds its first match, it will search the entire string and find all matches. There'll be plenty of examples of using flags throughout this tutorial. Let's start with a simple example, an expression that consists of the tokens T followed by H followed by E. Now, this will match the first occurrence of the characters T followed by H followed by E in the string. As we can see, the engine has found a match here on the first line. But what if we want the engine to find all matches? As we discussed earlier, we can do that by enabling the global flag. Now we can see the engine has searched the entire string and it has found all matches. Let's try a different expression. The tokens I followed by N. We can see that the engine has searched the entire string and has found all matches, apart from the I and N at the beginning of the string. You've probably also noticed that the I in the expression is lowercase and the I at the beginning of the string is uppercase, and the case insensitive flag is not enabled, meaning they don't match. But if we enable that flag, which we can see is enabled now because there is an I following the forward slash at the end of the expression, the I followed by N at the beginning of the string now matches the I followed by N in the expression, even though the I's are a different case. The I in the expression is lowercase and the I in the string is uppercase. I'm going to disable the case insensitive flag. Okay, let's talk a bit about how the engine performs a search. The engine starts at the beginning of the string and the beginning of the expression. It will then move through the string one character at a time and compare the character in the current position of the string to the token in the current position of the expression. So it will start at the I in the string and the I in the expression. If they match, the engine will move to the next character in the string and the next token in the expression. If they don't match, the engine will move to the next character in the string, and if it is not at the beginning of the expression, it will return to the beginning of the expression and start from the first token. There are exceptions to this. For example, if the token in the expression has a quantifier applied to it. What I've explained now is the basics of how the engine performs a search. As I introduce new tokens, I'll explain how the engine performs a search for expressions that contain those tokens. Let's step through a simple example. So the engine will start from the beginning of the string, which is an I, and the beginning of the expression, which is also an I. It will compare them using a case sensitive comparison because the case insensitive flag is not enabled. They do not match, so the engine will then move to the next character in the string, which is an N, and it will stay at the beginning of the expression. It will then compare the N in the string to the I in the expression. They also don't match. So the engine will move to the next character in the string, but it will stay at the first token in the expression. The engine will continue to move through the string one character at a time until it finds a lowercase I, which the first is in the word universe. The engine will then move to the next character in the string, which is a V, and the next token in the expression, which is an N. It will compare them, and of course they do not match. The engine will then continue in the string at the character after the first character in the most recent match attempt. The first character in the most recent match attempt was an I, so the engine will continue from the V in the string and it will move back to the beginning of the expression. It will compare the V in the string to the I in the expression. Of course they don't match, so the engine will continue to move through the string one character at a time until it finds an I to match the I at the beginning of the expression. The next I is in the word swirl, but the following character is an R, which doesn't match the following token in the expression. So the engine will then continue to move through the string one character at a time. And each time it matches an I, unless the N also matches, the engine will continue to move through the string and back to the beginning of the expression until it finds a match for both tokens, which the first match is in the word containing, where the I in the string matches the I in the expression. Then the engine moves forward to the next character in the string, which is an M, and the next token in the expression, which is also an N. They also match, so now the entire expression has been satisfied and the engine has found its first match. Because the global flag is enabled, the engine will continue to move through the string and search for more matches until it reaches the end and has found all matches, which we can see. There are many matches for the expression I followed by M. Now that you have a basic understanding of how the engine searches a string, let's talk about special characters. Special characters, as the name suggests, have a special meaning. There are different types of special characters. The first type we're going to talk about are quantifiers. Now, a quantifier affects the number of times the preceding token matches a character in the string. For example, there's the plus quantifier, which means match one or more of the preceding token. So let's take a look. Now we have the expression R followed by E followed by the plus quantifier. The plus quantifier is applied to the E token, which means match one or more E's. So we can see that this will match R followed by E here, and I'm going to enable the global flag so the engine searches the entire string. So we can see it's found R followed by E here, R followed by E here, and many more. Now let's say, for example, we add more E's. The engine will match as many E's as it can, because the plus quantifier means match one or more of the preceding token with no upper limit. So we can see here, it's matched all of these E's and it will continue to match as many as it can. Now, by default, the quantifiers are greedy, which means, as I mentioned, they'll match as many times as they can. But let's say, for example, we want to match the least times possible, right? We can add the question mark character after the plus quantifier. Now that turns the quantifier from greedy to lazy, meaning instead of matching the most times it can, it will match the least times it can. Now we can see it's found lots of these matches of R followed by E, but here, even though there are many E's for it to match, it has only matched one, because that's the least it can. Because remember, the plus quantifier means match one or more. So one is the least times it can match and the expression be satisfied. Satisfied means the expression matches the characters at the current position in the string. So as well as the plus quantifier, the second quantifier we're going to talk about is the star, and that means match 0 or more of the preceding token, again with no upper limit. So we can see now occurrences of R in the string match, but also occurrences of R followed by E match, and occurrences of R followed by multiple E's match, and it will match as many E's as it can. The star quantifier can also be turned from greedy to lazy. Now we can see we've added the question mark after the star quantifier, making it lazy, and even though there are E's for it to match, here there are multiple E's, here there's one E, here there's one E, it only matches the R, because matching 0 of the preceding token is perfectly valid and it's lazy, so it's going to match as little times as possible. The next quantifier is a question mark, and that means match 0 or 1 of the preceding token, effectively making it optional. So we can see here it matches R, here it matches R followed by E. Again, the question mark quantifier can be turned from greedy to lazy by adding a question mark after it. Now we can see it only matches the R, even when there is an E for it to match. The final quantifier consists of an opening brace followed by a closing brace, and either a single number between them, a single number followed by a comma, or a single number followed by a comma followed by another number. If there's only one number, then it means match exactly that many of the preceding token. So for example, I've added a 3 between the braces, and that means match exactly 3 of the preceding token, which is an E. So we can see here, it's matched R followed by E followed by E followed by E. But occurrences of R followed by E no longer match. And let's see if we add a number followed by a comma. Now this means match this many or more. So in our example, it matches 3 or more of the preceding token. So we can see here, it's matching multiple E's, right, with no upper limit. And if we was to change the 3 to a 1, now it matches R followed by one E, but also R followed by multiple E's. And if there's two numbers, it means match between the number to the left and the number to the right, inclusive. So in this example, it will match between 1 and 6 E's, but no more. And again, this quantifier is also greedy, but if we want to make it lazy, we add a question mark after it. Now, even though there are multiple E's for it to match here, it only matches 1, which is the least it can match. So you might be thinking, if the quantifier is lazy, meaning match the least times possible, what will cause it to match more than the minimum amount of times it can? So let's say, for example, we have the star quantifier and we make it lazy. So by default, it's matching 0 times, right? But let's say we want to make it match more than 0 times. We can, for example, make it so that if the E in the expression didn't match the E in the string, then the rest of the expression would not match. So for example here, I've got the expression with the tokens M followed by E, followed by a lazy star quantifier, followed by ANING. Now if the E, that is the second token in the expression, didn't match the E that is the second character in the word meaning within the string, then the rest of the expression, ANING, would not match the rest of the word meaning in the string. The next type of special character we're going to talk about is an anchor. Now, instead of matching a character, an anchor matches a position. The first anchor is the caret, and when used at the beginning of the expression, matches the position at the beginning of the string, or if the multi-line flag is enabled, it matches the position at the beginning of each line. So we can see here, because we've got the caret anchor at the beginning of the expression, it matches the position at the beginning of the string, and the following tokens, REG, will only match REG at the beginning of this string, right? Even though we have REG here, it won't match. It will only match REG at the beginning of the string, right? And there's also REG here, which is not matched because the position before the characters REG here does not match the caret at the beginning of the expression. If we enable the multi-line flag, we can see now the caret matches at the beginning of each line. So it matches this position at the beginning of the first line. It also matches this position at the beginning of the second line, but it doesn't match the position within this line before the R here. Now, another anchor is the dollar symbol, which when used as the last token in the expression matches the position at the end of the string, or if the multi-line flag is enabled, the position at the end of each line. So we can see the multi-line flag is not enabled, so characters does not match. Right, characters here doesn't match because it's not at the end of the string, and characters here also doesn't match because it's not at the end of the string. Now if I enable the multi-line flag, we can see here characters matches here because it's at the end of the line. So it means the position after it matches the dollar symbol anchor. But the word characters here does not match because the position afterwards does not match the dollar symbol anchor because it's not at the end of a line. The third type of anchor is a word boundary. 3 different positions qualify as word boundaries. The position at the beginning of the string if the first character in the string is a word character. A word character is any alphanumeric character and an underscore. So any alphabet character from A to Z, any digit from 0 to 9, and any underscore are considered a word character. The second position that qualifies as a word boundary is the position at the end of the string if the last character in the string is a word character, and the third position that qualifies as a word boundary is the position between 2 characters if one of the characters is a word character and the other is a non-word character. So for example, the position between a space and an alphabet character, or a full stop and a number. What word boundaries allow you to do is to match whole words. So for example, here we have a word boundary followed by the tokens THE followed by a word boundary. So this will only match occurrences of the characters THE when they form a word, not when they're part of another word. So we can see here it matches because the position before the T is a word boundary, because we have a space then a T. So the position between them is a word boundary, and at the end we have an E followed by a space. The position between them is also a word boundary. But the THE in the word mathematics does not match, because the position before the T is between two word characters, A and T, so it's not a word boundary, and the position after the E is between two word characters, so it is also not a word boundary. And in the word they, even though the position before the T is a word boundary, because it's preceded by a space, the position after the E is not a word boundary because it's between two word characters. The next special character is a dot. A dot matches every character apart from a new line, unless the single line dot all flag is enabled, and then the dot matches all characters including new lines. We're going to leave that flag disabled. Also, I'll mention there is no connection between the multi-line flag and the single line flag. The multi-line flag affects only the dollar symbol and the caret anchors, and they mean instead of matching the beginning of the string for the caret anchor and the end of the string for the dollar symbol anchor, the caret anchor matches the position at the beginning of each line, and the dollar symbol matches the position at the end of each line. And the single line dot all flag affects only the dot, and it means instead of the dot matching all characters apart from new lines, it matches all characters including new lines. The next special character is a backslash, and when it precedes a special character, it means instead of that character being special, treat it as a normal character. So when the backslash precedes a dot, for example, it means instead of the dot having a special meaning that is to match all characters apart from new lines, it has a literal meaning and it is just a full stop. The next special characters are the opening bracket and closing bracket, which enclose a character class. For example, the characters A followed by E. Now, a character class matches one of several characters. For example, let's say you want to find occurrences of the word grey in a string, but you want to find occurrences of the American English spelling and the British English spelling. You can have a character class with the characters A followed by E, and when the engine reaches the character class in the expression, it will match a character in the string whether it is an A or an E. For example, here we can see the expression matches G followed by R followed by E followed by Y, and it also matches G followed by R followed by A followed by Y. So in this example, the engine will match the character G to the token G. It will then match the character R to the token R. It will then compare the E to each character in the character class one by one until it finds a match or reaches the end of the characters. Now in this example, it finds a match when it compares the E to the second character in the character class. It then matches the Y in the string to the Y after the character class in the expression. And the same in grey with an A. The engine matches the G and the R. It then matches the A in the string to the A in the character class, and it then matches the Y in the string to the Y after the character class. You can also negate the class, which means instead of the character in the string matching one of the characters in the character class, the character in the string will match any character that is not in the character class. You can also have character ranges, for example A to Z or 0 to 9. There's a dedicated chapter to character classes where I go into a lot more detail. And the final special characters are an open and closed parenthesis containing a sequence of tokens. And what this does is creates a group. And for example, you can then apply a quantifier to the entire group. So if I add the question mark quantifier after the group here is a single token, and the question mark is applied to that token, i.e. the entire group. So here essentially it means match 0 or 1 of the preceding token, which is the group. So the expression will match REG, but it will also match REG-EX. Now let's move on to character classes. As mentioned, character classes consist of an opening bracket followed by a closing bracket and contain a sequence of individual characters and or character ranges. So let's say, for example, we wanted to match all opening HTML tags. We could have the character class like so, and then a second one like so. Apply a quantifier to the second character class, and then have a right angle bracket. So essentially here we have a left angle bracket which will match left angle brackets in the string. We then have a character class that has a character range A to Z, lowercase and uppercase. We then have a second character class that has A to Z, lowercase and uppercase, and 0 to 9. In other words, any alphanumeric character, followed by the star quantifier. In this example, the character class here is a single token, and the star quantifier is applied to it. So we can see here now the string has matched the tag head, and it will not match HTML tags that have attributes. It will only match HTML tags that start with a letter and then are followed by 0 or more letters and or numbers. So for example, it matches the head tag here, and I'm going to enable the global flag. It also matches the opening title tag, the opening body tag, the opening H1 tag, but it doesn't match the HTML tag because it has an attribute applied to it. Let's step through this example to see how the engine will search for this expression. So the engine will start at the beginning of the string, which is a left angle bracket, and the beginning of the expression, which is also a left angle bracket. It will compare them and see that they match. It will then move to the next character in the string, which is an exclamation point, and the next token in the expression, which is the first character class. It will then compare the exclamation mark in the string to every character in the character class one by one until it finds a match or reaches the end of the characters. Now, of course, in this example, it won't find a match because the exclamation mark is not one of the characters in the character class. So the engine will then continue from the character after the first character in the most recent match attempt. The first character in the most recent match attempt was the left angle bracket, so the engine will continue from the exclamation mark and it will return to the beginning of the expression. It will then compare the exclamation mark in the string to the left angle bracket in the expression. They do not match, so the engine will then move to the next character in the string and stay at the beginning of the expression. It will then move through the string one by one until it finds a character that matches the token at the beginning of the expression, which it finds on line 2. It will then move to the next character in the string, which is a H, and the next token in the expression, which is the first character class. It will then compare the H in the string to each character in the character class one by one till it finds a match or reaches the end of the characters. Of course, in this example, it does find a match because a H is within the character class. So the engine will move to the next character in the string and the next token in the expression, which is the second character class. Now, because this character class has the star quantifier applied to it, the engine will match it as many times as it can. So it matches the T, because the T is within the character class. It also matches the M and the L. But then the engine reaches the space, which does not match the character class. Because the character class is already matched enough times, it will not cause the expression to fail. The engine will then move to the next token in the expression, which is the right angle bracket, and it will stay at the same character in the string because the space has not been matched yet. It will then compare the space in the string to the right angle bracket in the expression. Of course, they do not match. However, the engine knows that the second character class matched more times than it needed to. So the engine will backtrack in the expression. Backtracking means moving to a previous token in the expression and potentially a previous character in the string, or releasing some of the matches of a quantified token. So in this example, because this character class which is quantified matched 3 characters and the minimum number of characters that it can match is 0, the engine will release one of its matches, right, which is the L. So now the second character class matches the T and the M, and the engine will compare the L to the right angle bracket. Of course, that doesn't match, so the engine will then backtrack further in the quantified token and it will release the M. So now the second character class matches the T only, and the engine will compare the M to the right angle bracket. They of course do not match. So the engine will finally backtrack one last time. The engine will then compare the T to the right angle bracket. They again do not match, and at this point the engine cannot backtrack any further because the second character class has now matched 0 characters. So the most recent match attempt has failed. The engine will then continue from the character one position after the first character in the most recent match attempt. The first character in the most recent match attempt was the left angle bracket, so the engine will continue from the H after it and from the beginning of the expression. It will then continue to move through the string one character at a time until it finds a left angle bracket to match the left angle bracket in the expression, which it finds at the beginning of the third line. The engine will then move to the next character in the string, which is a H, and the next token in the expression, which is the first character class. The H matches here, so the engine will then move to the next character in the string, which is an E, and the next token in the expression, which is the second character class. Because this token has the star quantifier applied to it, it can match an unlimited number of times. Therefore, it matches the E, the A, and the D characters, but it does not match the right angle bracket because the right angle bracket is not within the character class. The engine then moves to the next token after the character class, which is a right angle bracket. It then compares the right angle bracket in the string to the right angle bracket in the expression, and of course they match. The expression is therefore satisfied and a match has been found. The engine will then move through the string searching for further matches, which it finds here, here, and more throughout the string. Let's say you wanted to match all opening HTML tags or HTML tags that don't have a closing tag, including ones that have an attribute or multiple attributes. We can extend the regular expression and add a negated character class. So first we'll add a word boundary, then we'll add a negated character class. With a star quantifier applied to it. Now, As we discussed earlier, the word boundary will match a position between a word character and a non-word character. So for example, in this HTML tag, the word boundary will match the position between the L and the space, because the L is a word character, the space is a non-word character, therefore the position between them is a word boundary. Then we have the negated character class. The negated character class will match any character that is not within it. So if we continue stepping through this example, we know that the word boundary has matched the position between the L and the space. The engine will then move to the next character in the string, which is the space, and the next token in the expression, which is this negated character class. It will then check that the space is not within the negated character class. If the space is not within the negated character class, then it matches. Because the negated character class has the star quantifier applied to it, it will match as many times as it can. So the engine will then continue to move through the string one character at a time, checking that the current character is not within the negated character class. So it means the L matches the A, the N, the G, all the way to the right angle bracket. When the engine checks that the right angle bracket is not within the negated character class, that does not match because the right angle bracket is within the negated character class. The engine will then move to the next token in the expression after the quantified negated character class. The engine will then compare the right angle bracket in the string to the right angle bracket in the expression, and of course they match. At that point the expression is satisfied and the engine has found a match. The engine will then continue to move through the string, searching for more matches. Now the head tag still matches because the position between the D and the right angle bracket is a word boundary. So the word boundary token matches there. The negated character class can match 0 or more times. With the head tag, it matches 0 times. Then the right angle bracket in the expression matches the right angle bracket at the end of the head tag. The engine then continues, it finds another match here, finds all of these matches. We can extend this expression even further and match from the opening HTML tag to the closing HTML tag and everything in between. So to do that, we'll add another negated character class with the star quantifier applied to it. Then we'll add an expression that matches the closing tag. The reason why the forward slash has been escaped is because otherwise, if you was to copy this into code and the beginning and end of the expression were marked by forward slashes, having a forward slash within the expression will prematurely close it. Therefore, we escape it with a backslash. Now, we already know that up to this point matches the opening HTML tag, including any attributes. So this negated character class will match any character that is not a left angle bracket, and it has the star quantifier applied to it, meaning it will match as many times as it can. So in this match here, the negated character class matches everything up until before the left angle bracket. Then the engine will then move forwards in the expression to the token after the quantified negated character class, which is a left angle bracket. And it will move forward in the string to the next character, which is also a left angle bracket. So they match. Then the forward slash matches the forward slash. The T matches the first character class. The ITLE match the second character class because it has a star quantifier applied to it. And the right angle bracket matches the right angle bracket. At that point, the expression is satisfied and a match has been found. The engine continues and finds many more matches. Regex also has 3 shorthand character classes. There's \W, which matches any word character. As mentioned earlier, that is any alphanumeric character and an underscore. There is \D, which matches any digit from 0 to 9. And there's \S, which matches any white space. White space is a space character, a tab, a line return, a carriage return, and a form feed. There is also negated versions of the shorthand character classes, and instead of the lowercase letter, they use the uppercase letter. So instead of \W for any word character, it's \W for any non-word character. As we can see here, all the non-word characters are now matched. And instead of \D for any digit, there's \D for any non-digit. We can see everything apart from the digits is now matched. And finally, instead of \S for any white space, there's \S for any non-white space. As we can see, any character that is not a white space is now matched. The next thing I want to talk about is the dot. As previously mentioned, the dot is a special character that matches all characters apart from new lines, unless the single line .all flag is enabled, in which case the dot matches all characters including new lines. For this reason, the dot is very powerful and should be used sparingly. The majority of the time, there is a more suitable token than the dot. Let's look at some examples where the dot may seem like a good choice, but may not get the results you desire. Let's say, for example, we want to match dates that have a 2-digit month, day and year, and we want to be flexible with the separator. So the separator can be a space, a dash, a // or a full stop. You may use the following. And this will match dates like so. Now, looking at this example so far, it seems all good, but this regex will also match numbers like so, and that's probably not what you're after, because of course this is not a valid date. A more suitable regex would be something like this. So instead of the dot, we're now using a character class. I'll also take this opportunity to mention that when a dot is within a character class, it is not a special meaning, it's just a literal dot. This is still not perfect because it will match dates like so, which of course is invalid. How perfect you want your expression depends on its use case. For example, if you're searching for dates that you know are valid, so you're only really interested in matching their format, then this will probably suffice. But if you're validating user input, then you'll need something more advanced than this. Another example where the dot may seem like a good choice but may not be suitable is the following. Okay, so let's say you want to match HTML elements like the following. At first glance, this seems fine. It matches both of these elements. But what if you split the paragraph HTML element across multiple lines? We can see the dot no longer matches because it doesn't match new lines. Unless we enable the single line dot all flag, in which case the dot matches all characters including new lines, and now this expression matches the paragraph element even when it's split across multiple lines. But the single line dot all flag is not supported by all browsers. And even when it does match what we want, it is not the most efficient choice, because the dot will initially match everything from the H all the way to the right angle bracket. It will then fail to match the new line after the closing angle bracket, at which point the engine will then move forwards to the left angle bracket, and it will compare the left angle bracket in the expression to the new line character in the string. That comparison will fail. The engine will then backtrack in the dot and release one of its matches, which is the right angle bracket. The engine will then compare the right angle bracket in the string to the left angle bracket in the expression. That will also fail. The engine will then continue to backtrack in the dot's matches until it has released 4 more: the 1, the H, the / and the left angle bracket. At that point, the engine will then compare the left angle bracket in the string to the left angle bracket in the expression. They will match. Then the / will match the /, the H will match the first character class, the 1 will match the second character class, and the right angle bracket will match the right angle bracket. At that point, the expression has been satisfied and the match has been found. But if we were to change the dot to a negated character class, now the engine does not have to do any backtracking. The negated character class matches from the H to the D in hello world. The engine then moves forward to the left angle bracket in the string and the left angle bracket in the expression. They both match, and then the following 4 characters in the string match the following 4 tokens in the expression. No backtracking is required, and it is therefore more efficient. There's an example of when the dot is the most suitable token in the Backreferences chapter. The next topic is groups. Now, groups let you group tokens together. So, for example, you can apply a quantifier to the entire group. The group is a token by itself, but it also has subtokens. So, for example, here, the group from the opening parenthesis to the closing parenthesis is a single token, and the quantifier is applied to that token. But the E and the X within the group are also tokens, so can be thought of as subtokens within the group. This expression will match occurrences of the characters R followed by E followed by G, but it will also match occurrences of the characters R followed by E followed by G followed by E followed by X, because the E and the X within the group is optional. So let's step through this example. The engine will start from the beginning of the string, which is an R, and the beginning of the expression, which is also an R. They match. The engine will then move forward to the next character in the string and the next token in the expression, which are both E's and match. The engine will then move forward to the next character in the string, which is a G, and the next token in the expression, which is a G, and they match as well. The engine will then move forward to the next character in the string, which is a U, and the next token in the expression, which is the group. The group contains 2 subtokens. So the engine will then compare the U in the string to the E within the group in the expression. They do not match. But the engine knows that this group is optional because it has the question mark quantifier applied to it, which means match 0 or 1 of the preceding token. So matching 0 times is perfectly valid. So this expression is satisfied and a match has been found. The engine will then move forward to the next character in the string and back to the beginning of the expression, searching for more matches until it finds a capital R to match the R at the beginning of the expression, which it finds towards the end of the first line here. The R matches the R, the E matches the E, the G matches the G. The engine then moves to the E in the string and to the group in the expression. It then compares the E in the string to the E within the group and the X in the string to the X within the group. They both match. The expression is then satisfied and another match has been found. The engine will then continue to move through the string searching for more matches, of which it finds one more before reaching the end of the string. As well as applying a quantifier to the group, you can also apply a quantifier to one of the tokens within the group. For example, I can apply the star quantifier to the E within the group. Now, this will match things like we can see that because the star quantifier has been applied to the E, it means match 0 or more of the preceding token, which is the E. So here it has matched multiple E's, but it will also match 0 E's, 1 E, 2. It will match as many as it can, right, from 0 to no upper limit. There are two types of groups. The first is a capture group. And the reason why it's called a capture group is because the part of the string that matches the expression is stored by the engine and can be used, for example, in a back reference or to extract that part of the string. There is a dedicated chapter about back references where I go into a lot more detail. So let's just take a look here in the replace section of the regexr.com. Here we are using the dollar symbol followed by the group's number to access the part of the string that matches the group. So we can see in the first match here, the group does not participate in the match. So we can see here, nothing is captured. In the second match, the E and the X in the string match the E and the X in the group within the expression. Therefore, that part of the string is captured, and we can see it here. The same with the third match. Here is the captured part, and here is the part of the string that matches the group. And finally, the fourth match, the group does not participate in the match, and therefore nothing is captured. If you are not interested in storing the part of the string that matches the group, you're simply creating the group so that you can apply a quantifier to the entire group. You can turn the group from a capturing group to a non-capturing group, which is the second kind. And to do that, you add a question mark and a colon immediately after the opening parenthesis. Now we've turned this group from a capturing group to a non-capturing group, and we can see the dollar symbol followed by the 1 no longer references the part of the string that was captured because no part of the string was captured. The number following the dollar symbol will be the group's position. Because there's only one group, its position is 1. But for example, let's say there was 3 capturing groups. The first one would have the number 1, the second one the number 2, and the third one the number 3. Non-capturing groups would not participate in that numbering because the part of the string that matches them is not captured. So for example, if there was 3 groups, the first one is a capturing group, the second one is a non-capturing group, and the third one is a capturing group, the part of the string that matches the first group would be accessed using the dollar symbol followed by 1. With the second group, there is no part of the string that is captured because it's a non-capturing group. And the third group, which is a capturing group, the part of the string that matches that group would be accessed using a dollar symbol followed by 2. Because it is the second capturing group, non-capturing group does not participate because the part of the string that matches it does not get stored by the engine. Now, let's move on to anchors. There are three types of anchors, as mentioned in the special characters section. The first is a caret, which, when used as the first token in the expression, matches the position at the beginning of the string, or if the multi-line flag is enabled, it matches the position at the beginning of each line. So we can see here now the caret matches the position at the beginning of the string, and the following tokens reg therefore can only match at the beginning of the string. Even though we have reg here in the string and reg here, they do not match because they are not at the beginning of the string. So the position before the R does not match the caret at the beginning of the expression. So let's step through this example. The engine will start at the beginning of the string, and it will compare the position at the beginning of the string to the caret at the beginning of the expression. They match. The engine will then compare the R in the string to the R in the expression, and it will compare the E to the E and the G to the G, and then it's found a match. The engine will then continue to move through the string and search for more matches. Each time the engine moves forwards a character in the string, it will compare the position before that character to the caret at the beginning of the expression. They will not match because the caret only matches the beginning of the string. So the engine will not find any more matches. Now if we enable the multi-line flag, we can see now the engine has found a match at the beginning of the second line, because the caret, instead of matching only at the beginning of the string, it now matches at the beginning of each line. So we can see here the caret will match the position before the R at the beginning of line 2, and then the following tokens reg will match the following characters reg. But the word regex towards the end of the first line still does not match, because the position before the R does not match the caret at the beginning of the expression. Now let's say we have the following expression. The word characters followed by a dollar symbol. Now because the multi-line flag is enabled, the dollar symbol matches the position at the end of each line. We know if it was not enabled, the dollar symbol would only match the position at the end of the string. And now we can see no match for the expression is found because the tokens that precede the dollar symbol do not match the characters at the end of the string. Let's enable the multi-line flag again, and now we can see that the engine has found a match at the end of the second line because the tokens in the expression match the characters at the end of the second line, and the position at the end of the second line matches the dollar symbol. But the characters here, which match the tokens in the expression, do not result in another match because the position after the final character, which is an S, does not match the dollar symbol, because the dollar symbol again only matches the end of each line when multi-line flag is enabled, or the end of the string when it is not enabled. Let's say we have a caret at the beginning of the expression and a dollar symbol at the end of the expression. We still have the multi-line flag enabled. This means that the expression will only match if the entire contents of the line match the tokens between the caret and the dollar symbol. So let's see. Now it matches the first line, because everything from the token immediately after the caret at the beginning of the expression up until the token immediately before the dollar symbol at the end of the expression matches the characters from the beginning of the first line to the end of the first line. But if we disable the multi-line flag, now it no longer matches, because now the expression will only match if the tokens between the caret at the beginning of the expression and the dollar symbol at the end of the expression match the characters from the beginning of the string to the end of the string. The third anchor is a word boundary. And 3 positions in the string qualify as a word boundary. The first one is the position at the beginning of the string if the first character in the string is a word character. The second one is the position at the end of the string if the last character in the string is a word character. And the third one is between 2 characters if one of them is a word character and one is a non-word character. A word character is any alphanumeric character and an underscore. So that is any character from A to Z, 0 to 9, as well as an underscore. The word boundary token consists of a backslash followed by a B. And it allows us to match whole words. So we can see here we have the expression that starts with a word boundary, then has the tokens T, H, E, then finally another word boundary. And now this will only match characters T followed by H followed by E in the string when they form a single word, not when they're part of a larger word. So for example, we can see it matches the here and the here because the position before the T is a word boundary and the position after the E is a word boundary. Because there's a space before the T, which means the space is a non-word character, the T is a word character, so therefore the position between them is a word boundary, and the E is followed by a space. The E is a word character, the space is a non-word character, so the position between them is a word boundary. But the characters T followed by H followed by E in the word they do not match because the position between the E and the Y is not a word boundary due to the E being a word character and the Y also being a word character. Also, the characters T followed by H followed by E in the word either do not match because the position between the I and the T is not a word boundary and the position between the E and the R is not a word boundary. Let's step through this example to gain a better understanding of it. So the engine will start at the beginning of the string and the beginning of the expression. It will compare the position at the beginning of the string to the token at the beginning of the expression, which is a word boundary, and it matches because the position at the beginning of the string is a word boundary if the first character in the string is a word character, which it is. The engine will then move forwards in the expression and compare the R in the string to the T in the expression. They of course do not match. So the engine will then move forwards to the next character in the string, which is an E, and back to the beginning of the expression. It will then compare the position before the E in the string to the word boundary token. They do not match. The engine will then move through the string one character at a time, searching for a match. The next position that matches the word boundary is the position between the space and the R. But the space does not match the T, so that match attempt fails and the engine continues to move through the string. Finally, it gets to the character T towards the end of the third line, at which point the position before the T matches the word boundary because it is preceded by a space, which is a non-word character, and the T is a word character. Then the T, the H and the E in the string match the T and the H and the E in the expression. And finally, the position after the E matches the word boundary at the end of the expression, and the expression has been satisfied and the match has been found. The engine will then continue to move through the string searching for more matches, of which it finds one more before reaching the end of the string. Regular expressions allow alternation, and alternation essentially matches one of several expressions separated by a pipe. So for example, let's say you wanted to match occurrences of upload as well as download. You can use the pipe symbol, which means match everything to the left of the pipe symbol or everything to the right. Now, if I disable the global flag, we can see the engine finds a match for the first option, which contains the tokens UPLOAD, and of course that matches the characters UPLOAD. The engine will then stop searching. But if we re-enable the global flag, we can see the engine has continued to move through the string and found another match for the first option on line 2, and it has found 2 matches for the second option, the first one on line 3 and the second one on line 4. You can add additional options by adding more pipe symbols. For example, let's say we also wanted to match upload file as well as download file. Now here, the order is important because once the engine finds a match, it won't try to better that match. It will just move through the string to search for more matches. So because the expression upload is the first option, once that matches, even though there is another option that will match more characters on the second line, the engine will not try and improve on the match. It will just accept that match and continue searching for more matches. So here we would have to move upload file to before upload because it is more specific, and download file to before download. Now the engine will try upload file before it tries upload, and download file before it tries download. So let's step through this example. The engine will start at the beginning of the string and the beginning of the expression. It will compare the character at the beginning of the string to the character at the beginning of the expression and see if they match. In this example, they do match. Then the P, the L, the O, the A and the D match the P, the L, the O, the A and the D. But the next character in the string, which is an opening parenthesis, does not match the next token in the expression, which is an F. So that match attempt fails. The engine knows that there are more options, so it then moves to the second option and continue from the first character in the most recent match attempt. The first character in the most recent match attempt was the U at the beginning of the string, so it will compare the U at the beginning of the string to the U at the beginning of the second option in the alternation. They match. The P, the L, the O, the A and the D characters in the string match the P, the L, the O, the A and the D tokens in the second option within the expression. The engine has now found a match and it will continue to move through the string searching for more matches. It will compare the opening parenthesis to the token at the beginning of the expression. They do not match. It will then move to the second option in the expression and it will again compare the opening parenthesis in the string to the token at the beginning of the second option. They do not match. It will then move to the third option, which also does not match, and finally the fourth option, which also does not match. The engine will then continue to move through the string searching for more matches. The next match it finds is at the beginning of the second line, where the U at the beginning of that line matches the U at the beginning of the first option in the expression. The P, the L, the O, the A and the D, the F, the I, the L and the E match the following tokens in the first option in the expression. At that point, another match has been found and the engine will move forwards in the string searching for more matches. It then finds a match at the beginning of the third line, which matches the fourth option in the alternation. And it finds a match at the beginning of the fourth line, which matches the third option in the alternation. But this expression could be improved. For example, because the beginning 6 tokens in the first option within the alternation are the same as the 6 tokens in the second option, we can simply combine them into a single option and have the tokens FILE within a group that is optional. Now the first option in the expression will match the word upload file, but it will also match the word upload because the tokens FILE are within a group that has been made optional, because it can match 0 or 1 time, meaning 0 matches of this group is perfectly valid. And we can do the same for download and download file. Now, the word download file in the string matches the second option in the alternation, but also the word download in the string matches the second option in the alternation because the group that contains the tokens FILE has been made optional. Because the group at the end of the first option and the group at the end of the second option are the same, we can improve this further. Now we have put the alternation within a group, which means match everything to the left of the pipe symbol within the group or to the right of the pipe symbol within the group, and we've then followed it with an optional group containing the tokens FILE. This means that the first option in the alternation will match, the second option in the alternation will match, and either of those options can be followed by FILE. As we can see here, upload matches, download matches, upload followed by file matches, and download followed by file matches. We briefly touched on backtracking earlier. Now we're going to look into it a bit deeper. So backtracking is when the engine moves to a previous token in the expression and potentially a previous character in the string, or it backtracks in a quantified token, which means it releases some of the characters that matched the token. For example, let's say you have the dot token that has the star quantifier applied to it, which means match 0 or more of the preceding token. And then let's say the dot matched 10 characters in the string. Backtracking would mean releasing some of the characters from that dot's matches. So instead of it matching 10, release one of its matches so it now matches 9. Or release 2 so it matches 8. Or release 3 so it matches 7. And the engine can continue to backtrack until the quantified token matches the minimum number of required characters. So for example, if it has the star quantifier applied to it, the minimum number of matches is 0, so it can release all of its matches. If it has the plus quantifier applied to it, the minimum number of matches is 1, so it can release all of its matches apart from 1. Now let's see some examples. Say we had the following expression. Now we can see that this expression matches HTML elements. For example, this paragraph HTML element on the first line. The beginning of the expression matches the opening tag. The quantified dot token matches from the T here to the T here, and then the last part of the expression matches the closing P tag. Let's step through this example so we can understand how the engine finds this match and the backtracking that it performs. So the engine will start at the beginning of the string and the beginning of the expression. The left angle bracket at the beginning of the string matches the left angle bracket at the beginning of the expression. The P matches the first character class. The right angle bracket does not match the second character class, but because the second character class has the star quantifier applied to it, 0 matches is fine. The engine then moves to the right angle bracket in the expression and it compares that to the right angle bracket in the string. They both match. The engine then moves to the next token in the expression, which is the dot, and the next character in the string, which is the T. It then compares them, and because the dot matches all characters apart from new lines, they of course match. The engine moves to the next character in the string, which is a H, but because the dot has the star quantifier applied to it, which means match 0 or more times, it will match as many times as it can. So everything from the H to the closing right angle bracket match the dot. The engine then moves to the next character in the string, which is the new line character, and the next token in the expression, which is the left angle bracket. They do not match. The engine remembers that the previous token, which is the quantified dot, matched more times than it needed to. So the engine will backtrack and release one of the dot's matches, which is the right angle bracket. It will then compare the right angle bracket in the string to the left angle bracket in the expression. They do not match. The engine will then backtrack again and release another one of the dot's matches, which is the P. It will then compare the P in the string to the left angle bracket in the expression. They also do not match. So the engine will backtrack again and release another one of the dot's matches. And it will continue to release its matches till it releases one that matches the left angle bracket in the expression, which happens after the fourth character released from the dot's matches. Then the engine will move forwards in the string to the / and in the expression to the / they match. The P then matches the character class. The right angle bracket does not match the second character class, but again, because it's got the star quantifier applied to it, it means 0 matches is fine. The engine then moves forward to the right angle bracket in the expression, compares it to the right angle bracket in the string, they match, the expression is satisfied and the match has been found. So we can see in this example, the engine backtracked and released some of the dot's matches. But what if we change the quantifier applied to the dot from greedy to lazy by adding a question mark after it? Well, firstly, we can see for HTML elements that contain child elements, what has matched has changed. Because previously, on the first line, everything matched from the opening p tag to the closing p tag. Now, the match ends at the closing em tag, which is a child element of the p tag. So let's step through this example. We know that the beginning of the expression matches the opening HTML tag. So then we get to the T and the dot. The dot has the star quantifier applied to it, but it's been made lazy, which means it will match as least times as it can. Therefore, the engine will not attempt to match the dot, and it will move forward to the next token after the quantified dot, which is a left angle bracket, and it will compare that to the T. They do not match. At that point, the engine will know that the preceding token, which is the quantified dot, could have matched more characters than it did. So the engine will backtrack in the expression to the dot, and it will compare the dot in the expression to the T in the string. They match. Now the engine will move forward to the next character in the string, which is a H, and because the dot has a lazy quantifier applied to it, it will not attempt to match it to the H. It will instead move forwards in the expression to the token after the quantified dot, which is the left angle bracket. It will then compare the left angle bracket in the expression to the H in the string. They do not match. So the engine will backtrack again to the dot and compare the dot to the H. They match. the engine will move forward to the next character in the string, which is an I, and to the next token in the expression, which is a left angle bracket. The engine will continue to do this, moving forwards, failing to match the left angle bracket, then backtracking to the dot and having the dot match an additional character. It will continue doing this until it reaches the left angle bracket in the string, which matches the left angle bracket in the expression. The engine will then move to the next character in the string, which is an E, and the next token in the expression, which is a /. It will compare them and they do not match. The engine will then backtrack again to the dot in the expression and to the left angle bracket in the string. It will then compare them, they match. The engine will move forwards in the expression to the left angle bracket and in the string to the E and compare them, they do not match. The engine will then repeat the process it done earlier of attempting to match the left angle bracket in the expression to the character in the string, that failing, and then the engine backtracking to the dot and having the dot match the character. That will continue until the engine reaches the left angle bracket in the string, which matches the left angle bracket in the expression. It will then move forwards to the / in the string and the / in the expression, they match. Then the E matches the first character class, the M matches the second character class, and the right angle bracket matches the right angle bracket. The expression is now satisfied and the match has been found. As we saw earlier, when the engine finds a match, it will not attempt to improve that match. It will either stop searching, or if the global flag is enabled, it will continue moving through the string searching for more matches. Which is what happens in this case, and we can see it finds 2 more matches before reaching the end of the string. So now we've seen that when a token has a greedy quantifier applied to it and it matches more tokens than it needs to, if the engine backtracks, it means releasing some or all of the characters that match the quantified token. But when the quantifier applied to a token has been made lazy, meaning the token has matched less characters than it could, the engine will backtrack and increase the number of characters matching the token. So we can see here, each time the engine backtracked, it increased the number of tokens matching the quantified dot because the quantifier applied to it has been made lazy. But if we remove the question mark, making it greedy, now when the engine backtracks, it releases some of the characters that matched the quantified dot. Earlier, we spoke about capture groups and how they can be used in backreferences. So let's expand on that. A backreference matches the same characters as a previous capture group. Let's say we wanted to match HTML elements from the opening tag to the closing tag, including any child elements. We could use the following expression. Here we've used the capture group to store the part of the expression that matches the HTML element's name in the opening tag. We then use a back reference to the part of the string that matches the capture group to match the HTML element's name in the corresponding closing tag. Let's step through this match to gain a better understanding of it. The engine matches the left angle bracket in the string to left angle bracket in the expression. It then moves forward to the next character in the string, which is a H, and the next token in the expression. The engine is now within the capture group. The first token in the expression is a character class. The engine will compare the H in the string to each character in the character class one by one until it finds a match or reaches the end of the characters. Of course it does find a match because the H is within the characters in the character class. The engine then moves forward to the next character in the string, which is a 1, and the next token in the expression, which is another character class. The 1 in the string matches the character class in the expression. The engine then moves forward to the next character in the string, which is a right angle bracket, and the next token in the expression, which is a word boundary. The engine then matches the position before the right angle bracket in the string to the word boundary. The engine then moves to the next token in the expression, which is a negated character class containing the right angle bracket. The engine then checks whether the right angle bracket in the string is within the right angle bracket in the negated character class. Because it is, the match fails. Because remember, with a negated character class, a character in the string will match the negated character class if it is not within it. And because the right angle bracket is within the negated character class, it does not match. However, the negated character class has the star quantifier applied to it, which means 0 matches is perfectly fine. So the engine moves to the next token after the negated character class, which is the right angle bracket, and it stays at the same character in the string because the right angle bracket in the string hasn't been matched yet. It compares them. They of course match. The engine will then move to the next character in the string, which is a T, and the next token in the expression, which is a dot. They match. The engine will then move forward to the next character in the string, which is a H, and because the dot has a star quantifier applied to it, which means match 0 or more times, and the star quantifier is greedy, which means it will match as many times as it can, the engine will continue to match the dot as many times as it can. So the dot matches the H, the E, all the way to the end of the line, at which point the engine compares the new line character at the end of the line to the dot. They do not match because the dot matches all characters apart from new lines, unless the single line dot all flag is enabled, of which it isn't at this time. So the engine then moves forward to the next token in the expression, but stays at the same character in the string because the new line hasn't been matched yet. It then compares them. That match fails because the new line does not match the left angle bracket. However, the engine knows that the dot preceding the left angle bracket matched more times than it needed to. So the engine will backtrack and release one of the dots matches, which is the right angle bracket. It will then compare the right angle bracket in the string to the left angle bracket in the expression. They do not match. So the engine will backtrack even further and release another one of the dots matches, which is the 1. It will then compare the 1 in the string to the left angle bracket in the expression. They don't match. The engine will then backtrack again and release another one of the dots matches, and it will continue to do that until it reaches the left angle bracket at the beginning of the closing H1 tag, and that then matches the left angle bracket in the expression. Then the / in the string matches the / in the expression. Then the engine moves to the H in the string and to the back reference in the expression. The back reference here matches the same text as matched by the capture group. We know that the capture group matched H1, so the back reference will also match H1. Then the engine will move to the right angle bracket in the string and the right angle bracket in the expression. They match. Now the expression has been satisfied and the engine has found a match. The engine will then move forward to look for more matches because the global flag is enabled. When using back references, you use a / followed by the number that is the capture group's position in all of the capture groups. So for example, because there is only one capture group, it's Backreferences /1. But let's say there was a second capture group that we wanted to store a back reference to. The back reference will be /2. If there was a third capture group, it will be /3. It's always a backslash followed by the group's position in all of the groups, but only the capture groups. Non-capturing groups do not participate in back references, because when the engine encounters a capture group, it will store the part of the string that matches that capture group, and that allows that part of that string to be used in a back reference as we are using here. But if the group is turned from a capturing group to a non-capturing group, then the part of the string that matches the group, which is now a non-capturing group, is not stored by the engine, so therefore cannot be used in back references. And to turn a group from a capturing group to a non-capturing group, we add a question mark followed by a colon immediately after the opening parenthesis. And now we can see this no longer matches, because we are using a back reference to a captured group that doesn't exist, because this is no longer a capturing group, it is now a non-capturing group. The final regex feature that I'm going to explain is Lookahead and Lookbehind. Lookahead matches characters in the string based on the characters that follow them, and Lookbehind matches characters in the string based on the characters that precede them. Let's start with positive lookahead. Let's say, for example, we want to match occurrences of the character O only when it is followed by a K, but we do not want the K to be part of the match. In this example, we have a positive lookahead that contains the token K. A positive lookahead consists of an opening parenthesis, a question mark, an equal symbol, the tokens that we want to check for, and the closing parenthesis. So we can see this expression will only match an O when it is followed by a K. We can see here we have an O that is followed by an R that does not match. So let's step through this example and look a bit closer. We'll start from this O at the beginning of lookahead, which matches the O in the expression. The engine then moves forward to the next character in the string, which is an O, and the next token in the expression, which takes it to within the positive lookahead. It then compares the character in the string to the token in the expression. The character in the string is an O, the token in the expression is a K. They do not match. The positive lookahead then returns false, and the most recent match attempt has failed. The engine will then continue to move through the string, starting from the character after the first character in the most recent match attempt. The first character in the most recent match attempt was an O. So the engine will continue from the character after, which is also an O, and the beginning of the expression. It will then compare the O in the string to the O at the beginning of the expression. They match. The engine will then move forward to the next character in the string and the next token in the expression, which takes it to within the positive lookahead. It will then compare the character in the string, which is a K, to the token in the expression, which is also a K. They match. The engine will then move forward to the next character in the string, which is an A, and it will see that it has reached the end of the positive lookahead. At that point, the positive lookahead will release its match, which is the K, and it will return success because it successfully matched. Now, because the K has been released, the engine will move back in the string to the K, and the expression has been satisfied and the match has been found. So we can see here in that example, the match only contains the O, because although the K initially matched the positive lookahead, that match was released. The positive lookahead does not participate in the overall match. It simply checks the character or characters match the token or tokens within the positive look ahead, and then afterwards it will release any matches and return the result, either success if the tokens matched the characters or failure if they didn't match. Just to make that point more clear, if I add a token after the positive look ahead, let's say I add an A, now the O within look ahead, even though it's followed by a K, it does not match the expression anymore, because essentially the K in the positive look ahead and the A following the positive look ahead are both compared to the same character in the string, which is the K. Firstly, the O in the string matches the O in the expression, then the K in the string matches the K in the positive look ahead. The engine then moves forward to the A in the string. It sees that it's reached the end of the positive look ahead, so the positive look ahead releases its match, which is the K, and returns success. Because the positive look ahead has released its match, the engine moves back to the K in the string, and it moves forward to the A in the expression. It then compares the K in the string to the A in the expression, which of course fails, and that means the expression has failed to match the characters at the current position in the string. That means that the token in the positive look ahead and the token that follows it are compared to the same character in the string. So if the token in the positive look ahead and the token that follows it are different, then the expression cannot find a match. It's impossible, because they're both going to be compared to the same character. So if they're different, they can't match the same character. And if they're the same, let's say we add a K afterwards. Now this is pointless, because first the K in the positive look ahead will be compared to the K in the string. It will match, that match will be discarded, and the positive look ahead will return success. Then the K in the string will be compared to another token, which is also a K, and match. So the tokens in the expression, the K within the positive look ahead and the K after it, are being compared to the same string, and we can simply just remove the positive look ahead in that case, and it will match exactly the same thing. Let's say instead of a positive look ahead, which we have here, we want to match using a negative look ahead. To do that, we change the equal symbol to an exclamation point. Now this will match any occurrence of an O when it is not followed by a K. So we can see here it matches. So let's step through this match and explain it in more detail. The O in the string matches the O in the expression. The engine then moves forward to the next character in the string, which is an O, and the next token within the expression. It is now within the negative look ahead. It checks that the character in the string does not match the token in the expression. If they don't match, then the negative look ahead returns success. If they do match, it returns failure. Because remember, with a negative look ahead, the engine checks that the character does not match the token in the negative look ahead. And if they don't match, then the negative look ahead returns success. If they do match, it returns failure. So we can see here, an O when it is not followed by a K matches, and here an O when it is followed by an R, which isn't a K, matches, and an O followed by a D. But here where we have an O followed by a K, it does not match, because this expression means find all occurrences of O's when they're not followed by a K. The positive look behind is very similar to the positive look ahead. The only difference is it has a left angle bracket between the question mark and the equal symbol. Let's say we want to find all occurrences of an R when it is preceded with an O. We can use the following positive look behind. Now we can see it matches here because we have an R preceded by an O, and here an R preceded by an O. But here it does not match because the R is preceded by an E, and here the R is preceded by an E. This example will match all occurrences of an R when it is preceded by an O. Now what if we want to match all occurrences of an R when it is not preceded by an O? We can turn the positive look behind to a negative look behind by changing the equal symbol to an exclamation mark. Now this will match all occurrences of the letter R when it is not preceded by an O. So we can see here, R preceded by E match, R preceded by B match, R preceded by E match, R preceded by P match, but R preceded by O do not match. We've reached the end of the video. I hope you found this useful. I hope you have a much better understanding of how regular expressions work, the different types of tokens, special characters, how the engine performs a search, the different flags you can use. If you did find this useful, feel free to check out some of my other videos, and until next time, take care.